So welcome to lecture number 5 of electrical machines. Uh, in the last class, we discussed about the magnetic circuits, right? And also we discussed about the self-inductance and mutual inductance and how it plays important role in a coupling circuit, right? When there are many coils, they're connected together in series or parallel and they're magnetically coupled. So under that condition, how we'll find the equivalent inductance of the circuit already we have discussed. And today we'll see the magnetic losses in the system. So when magnetic material is being wrapped with a coil and it is being energized from the external source. So what kind of losses may happen in the magnetic material? Let us see today, and then we'll talk about little bit the principles of electromechanical energy conversion. Okay. So magnetic losses we'll talk about, and we know in the electrical machines when we do the analysis, performance analysis, this losses plays important role, and therefore the losses in the electrical machine, because when we are considering a machine, we give some input energy, we take some output energy in other form. Like suppose I'll consider a generator. In case of generator, I'll give the mechanical energy as the input and I'll take the electrical energy as the output. So in between, this conversion happens in the magnetic field, and there are certain losses takes place inside. So therefore, if we'll see the losses, therefore always when during the performance analysis we find the efficiency of a machine, we need to find out the losses. So usually the losses are divided into three major categories as mentioned here, right? So one is your copper loss, and second one is mechanical loss, and third one is your magnetic loss. Okay. So what is copper loss? Copper loss is nothing but this is the loss which is happening because of the flowing of the current in the winding or in the coil, right? So it is because of the resistance in the network when the current passes through. So this is nothing but the I square R loss, right? Okay. And this mechanical loss, if we'll see, this mechanical loss happens because of the friction in the bearing and also because of the windage loss, because of the wind friction in the rotor, right? So this is mechanical loss. Then what about the magnetic loss? In fact, this plays very important role, right? This magnetic loss, in fact, it has many components. Let us see. So this magnetic loss happens, in fact, in the magnetic material. Okay. So how it happens? Let us see. So the copper loss takes place in the winding of its machine. The mechanical loss arises from the rotation of the rotating part of a machine. It can be divided into three parts: bearing friction, brass friction, and windage. It is because of the wind friction. So there are two sources of magnetic loss. One is magnetic loss is also known as iron loss or core loss. Sometimes they are named as, sometimes if somebody says iron loss and core loss or core loss, you can say this is magnetic loss. So it has two components. One is the eddy current loss and other one is your hysteresis loss. Okay. Now let us see these two components. What are these two components? Eddy current loss and the hysteresis loss. So what is eddy current loss? In fact, this magnetic material is also a conductor, right? So whenever we are injecting the current around this coil, you are seeing this picture. So here, when the current is flowing, in fact, when the flux will produce, suppose this current is alternating and the flux produced inside this core will also alternating. And because of this alternating flux inside the core, that core will also produce an EMF in the core because it is a conducting material, right? So it will produce an EMF in the core itself. and because of that EMF, the current will produce, because it's a conducting material, so the current will produce in this fashion. Right, it is just enclosing the flux, because the flux path, if we'll see, this is your flux path, right, in the cross section, towards the cross section, and the circulating current will flow around this flux. Okay, and this is known as eddy current. So the name is given, in fact, eddy current, because we have seen the eddy current, in fact, it produces in the water and wind, like whirlpool, right? In the wind also we have seen, in the water also we have seen. So therefore this kind of whirlpool produces in wind and water. Similar structure is producing here. Therefore the name is given here eddy current, right? And so because of this eddy current, when it flows in this material, so it has certain resistance, and therefore it some loss occurs because of this eddy current, that also we call I square R loss. This R is the resistance to the path of the eddy current. So this gives us the eddy current loss. Okay. So now the question is how to reduce this eddy current loss. If we can we reduce this eddy current loss if we can make the path of this eddy current smaller and smaller, then we can obviously reduce this loss, this I square eddy current. I is nothing but the eddy current, IE, let us say. So the I square R we can reduce when we'll make the path to the eddy current smaller and smaller. So how can I make this path smaller and smaller? Only when we can laminate this core and insulate these laminations. Like if I can laminate this core, right? Like small sheets, thin sheets, I can make these thin sheets and combine together, stamp it together, and in between these two sheets I can put some insulator, right? So in the insulator the current will not flow, so only the current path will be inside this thin sheet, and by that way I can make the current path smaller and smaller, right? Like you can see here. So we have thin laminated sheets, right? They are stamped together, and in between we have the insulators. Okay, so these are the insulated layers. So therefore the eddy current will reduce by this way. Okay, so now this eddy current, if we'll find the eddy current loss in the equation form, this is experimentally determined, this equation. It is found that the eddy current is directly proportional to the frequency square of the frequency and the flux density square. Okay, so if we'll find in the experiment, it is found that it is P is directly proportional to F square and P is directly proportional to BM square, and obviously it will depend upon the volume of the material. So P is directly proportional to V. V is the volume of the material here, not voltage, right? And your delta is your thickness of the lamination. So P is also directly proportional to delta square. So now combining these four things, it is found the expression P equal to K F square delta square BM square V, and K is the constant of proportionality which depends upon the constructional structure of the material, right? Or on the material itself, the quality, the characteristic of the material, constructional feature and the characteristic. Okay, magnetic characteristic of the material. Okay, now coming to the hysteresis loss. So hysteresis loss, if we'll see the hysteresis loop here, hysteresis loop is nothing but it is the characteristic of B versus H. And already we know when there is alternating current will flow, we have the BH characteristic like this, right? BH curve. So when this BH curve will look into, if we can calculate the area under this BH curve, BH loop, right? That means the area covered by this, right? The whole area inside this BH loop, that will give us the hysteresis loss. we can see here. And if we'll find one part of this area, then other part we can just multiplying into 2, we can find it, right? So let us find first the area covered from BR to BM, that is the area with A, B, C, D and A, right? So the area covered under this is A, B, C, D, A, right? Say C, D, E, A, you can say E, A. Okay, so that means the whole area under this, right? So obviously we know the energy will be H dot dV, right? H is the, because H is directly proportional to current and B is directly proportional to voltage. So it will give us the energy, right? So therefore the area under this characteristic will also give us the loss, right? Power loss, that is hysteresis loss. So if we'll integrate from minus BR, this is the residual point, right? BR and minus BR. So residual flux or flux density, you can say. So minus BR to BM when we'll integrate H dot dV. So that will give me the whole area, this area, right? All this area. So now if I'll find this area and subtract this area only, I'll subtract this area, that is area under ECDE, right? If I'll subtract the area of ECDE, right? That is W2, that is mentioned in the W2. And this is the area, whole area covered by A, B, C, D, E, A. And the area which is enclosed under E, C, D, E, if we'll subtract both the area, that will give me the net area of this, right? This is the net area I want to find. And then if I'll multiply it with 2, I'll get the whole area under this BH curve, right? So now the net energy if we'll find, that is W equal to net hysteresis loss will be twice of W1 minus W2, right? So W1 is this minus W2. And in fact, it is very difficult to find analytically this the expression of hysteresis loss. So therefore, by experimentation, this can be possible, and therefore the Charles Stenmerge, one of the scientists, he in fact found through some experiment, various experiments he did, and he found one expression for hysteresis loss, and that can be expressed because W1 and W2 has no certain function. Here we cannot express H in terms of B, right? It is difficult. So H as a function of B, it is difficult to find a particular function in terms of B, right? So therefore, through experimentation, Charles Stenmetz has proposed the hysteresis loss as this: pH will be equal to kh f bm to the power n v, right? So that is magnetic loss is the sum of the, so total magnetic loss I can say is the sum of the eddy current loss and the hysteresis loss. So I can write, so note that the hysteresis loss doesn't depend upon the lamination thickness, but the eddy current loss depends. So for a given magnetic material, we can express the magnetic loss as this. So total magnetic loss I can express this is K F square Bm square plus Kh, capital Kh F Bm n, Bm to the power n. So whereas the capital K and Kh is defined as this. So capital K is nothing but small k del square V, and capital Kh is small kh V, right? So this is your final expression for the magnetic loss, or we say it iron loss sometime, right? Or core loss. Okay. So these are the terms we use sometime instead of magnetic loss. Okay. So now this is all about your magnetic loss. Now the question is how to find this magnetic loss through experimentation. If in your lab some experiment, I don't know whether it is there, it is I think not there to find out the segregate the losses. So you can find it with the experimental data. Suppose we have following data with a thin sheet silicon steel. Now let us compute the hysteresis loss and eddy current loss. Okay. So the data is given as follows. It is, we can see here, for different frequency, we measured the flux density and the magnetic loss. Okay. It is possible to measure because we can find this magnetic loss just by putting the wattmeter across the element, across the device of which we want to find the magnetic loss under no load condition, right? So we'll talk about it more in transformer part. Also, when we'll we'll study it, right? So now we found under the frequency 25 Hz and flux density 1.1, it is found that the magnetic loss is 0.4 watt per kg. And again, at frequency 25 and changing the flux density to 1.5, we found magnetic loss 0.8 watt per kg. And again, by increasing the frequency and keeping the flux density constant, we found the magnetic loss as 1.2. Now, the formula we know, the magnetic loss is KEF square Bm square plus KHF Bm to the power n. Now, in this formula, which are the parameters to be decided, to be determined? One is your K and KH. These are the variables we want to find. Okay, the parameters, because we know Bm, right? And F also is known, frequency is known. So only thing we want to know is K, KH and N, right? Steinmetz constant. Steinmetz constant is N. So we want to find K, KH, N. So there are three variables, and if we can write three equations using these three experimental data, then from these three equations I can solve, I can find these constants, these parameters K1, K, KH and N, right? After finding it, I can write the losses. I can determine the losses. So these are the three equations for magnetic loss, right? For different frequency and different flux density. So out of this, if we'll solve these three equations, we'll find K, KH and N. So after finding these parameters, I can substitute in respective loss equation. I will find the different losses, right? So it is found that by solving these equations, it is found K equal to 94.451 in 10 to the power minus 6 and N equal to 2.284 and KH equal to 0.0106. Now just substituting these parameters, I'll find for different frequency, different flux density, I can find the hysteresis loss and eddy current loss, right? And if we'll add this up, I'll sum it up, I'll find the total magnetic loss, which is equal to this 0.4, 0.8 and 1.2. Okay, this is how I generally segregate the hysteresis and eddy current loss. Okay, so okay, now let us move to the principles of
Excuse me,
electric.
sir.
Yeah,
Sir, why is the area under the hysteresis loop is considered as hysteresis loss?
I
Like, is
told
there any
you.
derivation for the same?
I told you this. You were, I think, inattentive. H is directly proportional to I, and B is directly proportional to V. We know VI is the power, right? Okay. So therefore, H
So,
dot
but that is
dB
like a kind of a surface information. Like, is there any kind of a proof which you can provide us?
proof means that is the
Like, yes, sir.
loss is obviously the loss we found based on voltage and current. When we found it is like VI, right? Whenever we found any power equation, that is VI, right? And V is here, V is
So, but this,
directly, yes,
but this certainly shows that this area under the loop is mainly energy. This doesn't show that the area under the loop is loss.
that energy is lost because you see when, in fact, if you'll see the analytical way, through the analytical way, this area, what this area indicates. In fact, the movement of
the
the
energy.
dipoles, right? When the dipoles move, right? Because they change their direction when the magnetic field changing the direction, right? So when the dipole
Yes, sir.
move, the molecules also move, right? And it creates friction inside the inside that material. So that causes, in fact, loss, magnetic loss. We can say it as molecular friction of the, because of the magnetic field, whatever molecular friction takes place inside the material, that is the loss, hysteresis loss. Okay, are you getting?
Sir, but still, sir, I'm not getting this thing that how the area is the loss. Like I'm getting that there will be a flux inside that solid core, that
Hmm.
core on which we are looping over. Uh, I get each and everything about that. So, but like how is this area is considering is showing us the loss? Like
That is what I told you. It is only
you're
analytically
making me
we can
understand.
understand. There is no such derivation. Analytically, we can say that
Okay, sir.
only molecular friction, because of that it happens, and this molecular friction will depend upon the magnetic field intensity, that is H, and the flux density. Okay. So obviously when we uh, because the area which is covered by this BH curve, right? So that will, in fact, I'll tell you in detail. You're asking analytically only we can uh, perceive it. So in detail, maybe I'll talk to you in the next class. Okay, little bit, because this is the concept of material science. I have to go into detail. Okay, so I'll tell you. Okay,
Okay, sir.
just remember
Okay, sir.
this.
Sure.
So maybe in the next class we'll
Thank
talk
you, sir.
about more. Okay.
Yes.
Okay. So this is your, already we found the segregation of KH and KE. Okay. Okay, now we'll talk about the principles of electromechanical energy conversion. Okay. So this electromechanical energy conversion plays very important role for us, because uh, any machine we see, like the motor and generator, they're based on this principle, electromechanical energy conversion, right? So when we, in a motor, we give the input as electrical energy, we get output as the mechanical energy, right? And in case of generator, we give the mechanical energy, we get the electrical energy output. Now the question is, if we'll see the performance analysis, obviously there are three kinds of energy working on it. One is input energy, one in the one form, and other form is output energy we get, and certain losses takes place inside the system, right? And also some change in the magnetic field takes place, that also uh, that also absorbs some energy. So like we can say that, so we will say that this is your energy structure. So we give the input energy, right? That is Wi, and we get here output energy, Wo, and we have inside the machine we have some lost energy and some stored energy, that is Wf, and the lost energy is Wl. Okay. In fact, this lost energy, it it is it goes out in terms of heat, mostly in terms of heat, right? So this is lost energy, and we cannot recover this, we cannot conserve this energy, right? So therefore in a conservative system, generally the loss is neglected. Okay, now we can see the equation, that is Wi is equal to Wo, that is output energy, plus lost energy, plus Wf, that is the stored energy in the magnetic field, because the magnetic field acts as the medium where the conversion takes place. from one energy, from one form of energy to other form of energy, right? So, but in case of conservative system, when the energy is being conserved, the loss is neglected. Okay. So the system is said to be conservative or lossless if the loss in the energy in the system is zero. Okay. So that means your input energy will become equal to output energy plus stored energy in the magnetic field. So obviously the field may be magnetic field or electric field. It depends upon the application. And here in the electrical machines, we are focused on the magnetic field because magnetic field will act as the medium through which the energy conversion takes place. So therefore, we'll consider here only the magnetic field analysis when only we'll consider the medium as a magnetic field. Okay. So here we have a conservative system. We can say, let us assume a conservative system here. We are assuming this is a lossless system. Okay. And we are connecting this coil, a voltage source V, and a current is being injected to the coil. So now in this conservative system, the electrical energy input in time dt will be how much? It will be, if you'll write the expression, it will be in time dt, it will be dwi, that is equal to vi dt. And I can write the same equation in terms of induced EMF because v is not nothing but it is equal to minus e. So I can write minus ei dt, right? And obviously E I know it is minus d lambda by dt. So lambda is your n phi. This is the flux linkage. If flux is phi in the core, right? And dw again I can write by substituting in terms of lambda, I can write it as I lambda, right? Okay, so dw will become I lambda, I d lambda, and that is nothing but equal to ni d phi. So this is for a conservative system, and here the output is also not there, output is also zero. That means whatever energy we are giving here as input, that is being stored in this in the magnetic field. Okay, hence the energy input to the set of to set up a flux phi t in an n-turn coil is this much, right? So energy input will be, I'll just take the integration, it will wi will be integration of I d lambda equal to n of integration I d phi. So in a conservative system with no output energy, I have told that the system where we are considering no output and the loss is also zero. So the energy supplied by the source must be stored in the system as magnetic energy. And in a linear system, the energy stored in the system is this. Already we know this, right? So we know that in a linear system, linear magnetic system, we know Wm will be equal to half of n phi I, and that is equal to half of Li square. And L we know is equal to n phi by I. So in a linear system, this formula applies, right? It is n d phi by di, but if the system is linear, then I can write n phi by I. So Ni is equal to HL. We know this because Ni is your MMF, which is nothing but equal to HL, magnetic field intensity, and the length through which the flux is passing. And d phi I know is A dB, right? Just by substituting Ni is equal to HL and d phi equal to A dB. So my expression will become, expression for the input energy will become La H of dV, right? So this is, I think this is the formula you are seeking, right? Who was asking this question? H dV, the energy. Somebody was asking, right? So how the hysteresis loop, H dB, the integration of H dV is the energy. So this is the formula, I think so. Okay, you got your answer. Hello. Somebody was asking, what is your name? Who was asking the question, integration of HdV, how it is energy? Is it there? Hello? Somebody was asking the question how HdV, the integration of HdV will be the energy. I think he got this answer through this expression. So we got the input energy here in this core, right? The input energy expression we got is La integration of HdV, right? I hope you got the answer. Who have raised the question how the integration of HdV gives the energy, right? So this is the expression which yields the energy that must be supplied to set up a flux density B in the magnetic core. So this is the energy required to set up a flux density B in the magnetic core. Now let us obtain the expression for the magnetic force in terms of the magnetic stored energy. Okay, magnetic stored energy is your Wm, right? So now we want to find the expression of force, that is F, right? So in terms of Wm, so let us find it. So there are two cases we'll consider here. One case is your constant flux case, and the second case we'll consider constant current case. So in the constant flux case, let us say the magnetic circuit is moved by a distance dx in time dt in a region where the flux is held constant. From from this equation, what will happen? From this equation, if we write the input equation, that is I d lambda integration in integration of I d phi. So the flux is being constant, so d phi will become 0 because the final flux value and the initial flux value, there is the difference will be 0 when there is a movement of dx distance. So therefore your Wi will become equal to 0, right? This will become equal to 0. Your Wi will be 0. Now your Wi is equal to nothing but, in a conservative system already we discussed that it is equal to Wm plus, sorry, this is your work. This is Wo plus Wm. Already we know this is equal to Wi, right? So now for the incremental distance displacement dx, so I can write dwi equal to dwo plus dwm, right? So dwi is 0. This will be equal to 0. So I can write dwo is nothing but fm dx plus dwm, that is equal to 0, right? So now from this equation, consequently the mechanical force will be how much? From this equation, the mechanical force will be Fm will be equal to minus of dwm by dx. Okay, so this is your expression which is mentioned in the next slide also, right? In the next slide also it is mentioned that the mechanical force acting on the magnetic circuit is this. Fm will be equal to minus dwm by dx. So now when the flux is held constant, this equation clearly shows that the rate of decrease in the stored magnetic energy, this is your stored magnetic energy, Wm, with respect to the displacement determines the force developed by the magnetic device. Okay, so this is when the flux is being held constant. So the negative sign indicates that there is a decrease in the magnetic stored energy when there is a displacement. That means when it moves, when your magnetic element material is moving by dx, right? So let us consider case 2. In case 2, we'll consider constant current. So in case of constant current, for a change in flux d phi and keeping current constant, how the energy input will look like. So your Wi will become equal to I d lambda integration, that is equal to n I d phi, right? So your phi is variable and your I is being constant. So I can write it this equation as dwi will be equal to I d phi, right? So let us mark this ni as, because I is a constant, I can take it as capital I. So it will dwi will become equal to I d phi, right? And we know dwm is, already we know the stored energy in the magnetic field is equal to half of I d phi, right? So Ni d phi, right? Ni d phi is nothing but I d phi, right? Capital I d phi, half of I d phi. So now substituting this in and writing this equation in terms of dWm, I can write dWi is equal to twice of dWm. So up to this it is fine. Now from this expression I can write that this is your input energy dwi, and dwi is nothing but equal to your dwo plus this is your dwo, this is your dwm. So right, so therefore I can write this as fm dx plus dwm, that is equal to twice of dwm, right? So now just simplifying this, I can find the expression for Fm, that is the magnetic force. Fm will be equal to dWm by dx, right? So now we have two expressions we found. One is when the flux is constant, your Fm is becoming minus of dy dx Wm, and when your current is being held constant, your magnetic force is becoming dy dx of Wm. So only the sign change. Here it is negative sign, it is here positive sign. So therefore, in the form of a function, if we'll write when the flux is constant, here the flux is constant, right? And x is variable, so I can write it Fm is equal to minus of partial derivative with respect to x, Wm phi x. And similarly, when the current is being constant, I can write the magnetic force like the partial derivative of Wm Ix as a function of Ix with respect to x. Okay, so these two expressions plays important role in finding the magnetic force in a magnetic circuit. Okay. So now let us move forward. Let us now express the magnetic force in terms of inductance of the magnetic circuit. Why it is important? Because in a linear magnetic circuit, we can calculate inductance very easily by calculating the reluctance, right? So it is only applicable to a linear magnetic circuit. So rate of change of the stored magnetic energy from the below equation when the flux is constant will be this. There is Wm, already we know the energy in the magnetic field is half Li square, that is nothing but equal to half of n phi I, right? And if I'll take the derivative with respect to x, it will become half of n phi delta partial derivative delta x of one delta I by delta x, right? So if I can substitute I in terms of L here, then obviously, so it is a linear circuit, so therefore I can write here I equal to nothing but, I can write it here. So you know L equal to n phi by I. So for linear system, I can write I equal to n phi upon L. Right now, substituting here in this expression and taking the partial derivative of I with respect to x, so I can write it here just by some manipulation. I can write it just like I can do it here, half of n phi delta x n phi by L. So I'm taking derivative of this. So now I'll find this as half of minus half of n phi square here, right? And if we'll take the derivative, because phi is constant here, right? So if we'll take the derivative of 1 by L with respect to x, it will be, sorry, it will be minus 1 by L square delta L by delta x. So this will give me minus n phi square by L square delta L upon delta x, and it will give me uh, half I square delta L upon delta x. Okay. So this is the expression of magnetic energy, stored energy in terms of L, sorry, the rate of change of the magnetic energy, that is in terms of L, right? So now if I'll find Fm from this expression, because Wm I know, and for constant flux linkage case, if I'll see, that is Fm is nothing but minus delta Wm by delta x. So just by taking the derivative, I can write it as, so already the derivative is here. So Fm will be half of I square delta L upon delta x. So that means this is the expression of the magnetic force in terms of the inductance. This is for a linear system and when the flux is constant. Okay. So this equation is also valid when the current is held constant. You can also derive the same expression taking current as constant. Okay. When current will be constant, the expression for Fm is what? It is dWm upon dx, right? So there is no minus sign. So keep current constant and vary flux, right? So here instead of current, you will take derivative, partial derivative with respect to flux, right? So that means when I take, I'll write delta omega m by delta x, I can write it as here half of Ni, because constant current is constant, so I can write half of Ni delta phi upon delta x. So now with respect to phi, I can change phi, and I can write expression of phi in terms of inductance and substitute it here and take derivative. And finally, I will find the same expression, that is nothing but half I square delta L upon delta x. Okay, the same expression I will get for constant flux linkage, for constant current case. For both the case, you will find the same expression, right? So that is what this is mentioned here, and this equation is quite simple to use for linear magnetic circuits because we can determine the inductance of the magnetic circuit using the reluctance concept. Okay, so now let us find the magnetic circuit with air gap. How we'll determine the magnetic force. Up to this point, we saw the derivation of magnetic force for a solid iron case because solid ferromagnetic material without an air gap. And we know in electrical machines, this air gap plays very important role because in every machine we'll see, like whether it is motor or generator, we'll find air gap because without air gap, there will be no rotational element, rotating element. So therefore air gap plays very important role. So we'll now find this force expression of the magnetic force with the air gap. So what happens when the air gap is there? Now we can see here there is a solenoid here and another piece of iron is here below this and with some air gap, and the distance between these two is x. Okay, and the cross sectional area is A here, right? And the number of turns in the coil N and the current injected is I. And this is your movable part, it can move, and this is your fixed part. Now we know this expression of input energy from last slide already we discussed. This is LA integration of HdB, right? And from this expression I can find the energy here, the energy input in this system to the air gap Wg, I can write half of mu naught h naught square Ax. How this expression came? Just by substituting the values, right? So we can substitute here dB, right? So just write the expression here. So here if we'll write LA integration of HO, So it is HO, and dV I can write it in terms of flux. It is nothing but I can write it as in terms of H. I will write mu O HO. So D of HO, right? Sorry, I can write mu O D of HO, right? So now your expression will become LaHO mu O, sorry, mu O integration of HO dHO, right? So this will give me La half of La mu O HO square. Okay. So this L is nothing but it is the air gap, so I can replace it as X. So I can write it as half of mu O HO square AX. So this is the expression here, right? And this is equal to, if I'll convert to this H into magnetic flux density in terms of magnetic flux density BO, this expression will get here again 1 by 2 mu O BO square AX, right? Okay, now we'll find the force, magnetic force. So the expression for magnetic force is, already we know that it is delta, uh, sorry, it is, and because the flux is constant here, I can write this as uh, minus of delta omega m by delta x, right? So just by taking derivative, because here omega I is so the output, so here your, sorry, if I'll write d omega o plus, sorry, dwo plus dwm equal to dwi, right? So your dwm is so dwo. So when it is in stationary condition, your dwo is 0, and under that condition your dwi is equal to dwm. So I can write it as this Fg is magnetic force. This Fg will be nothing but dwm by dx, delta wm by delta x. It is nothing but equal to minus of delta wi by delta x. So just taking the derivative of delta wi with respect to x, I'll get the expression minus of half mu naught ho square a, right? So again, we know it will become minus of half twice of mu naught bo square a, right? Okay. So this is what we got, and finally, the presence of the negative sign in this expression, in fact, shows that Fg is a force of attraction in the each of the air gap, right? That tends to decrease. Okay, that tends to decrease. So now we can see it. One problem. So this problem maybe we'll discuss in the next class, because now your time will not be sufficient to discuss. We'll discuss in the next class. Okay. So in the magnetic circuit of figure, there is a magnetic circuit we can see here, and just take this problem and we'll discuss in detail in the next class. Let us discuss. If you have any doubt, we can discuss now. Okay. So next class we'll talk about this. Okay. So thank you very much. So if you